Well, good morning. This is Thursday morning, the 3rd of November, 9:31 in the morning, and supposed to be Math 238, differential equations. And right now I'm the only one in the room, so I will go on and get started. Hopefully some people will be coming in shortly. Okay, I'm going to go close the door so I won't be bothering people up and down the hall. I'll be right back. Okay, I'm back. Sorry about the slight delay there. A couple of announcements first, and these do pertain to this class. Well, maybe somebody's coming. Yes, okay, we've got a student. Flip the lights if you would. Yeah. Okay, good. And hit the bottom button once on the way by. Got it. Okay.
No, I don't think so.
Okay.
How long have you been started?
Cameron's here. Huh?
How long have you been started?
Just a couple of minutes. Okay. I just was starting to make the announcements. I met with my first class this morning, and the folks that said they could come today at 12:30 can't. So we're going to do it Tuesday at 12:30, which is when we would have been doing the makeup for this class. So if we can, let's do the makeup for this class this afternoon. We got any time you choose to do it. We don't have to do it at 12:30.
What day are you going to be gone again?
Tuesday.
Next Tuesday.
I was going to make it up later in the day because I thought I was going to do my pre-cal classes, today, but they can't make it today and can make it Tuesday, so we'll do that. So if we want to eat lunch first, we can, and then come out and do this and get it over with. And that way you don't have to worry about coming in case I get through with treatment, with my doctor's appointment early.
Just don't worry.
Yeah, I won't do anything. We'll make up the whole class today, and then Tuesday we won't have class at all in differential equations.
Yeah.
We will do linear algebra stuff.
We will be here.
So there's that. Then of course that comes from the fact that tomorrow, related to the fact tomorrow I won't be on campus at all because I've got treatment from 6:30 in the morning labs to probably 4:30 in the afternoon. Hopefully I'll be through by then. Okay.
My grandmother is on the 3rd floor.
3rd floor. Oh, really? Okay.
Probably won't see.
No, probably won't. Okay.
Oh man.
I didn't know they had an infusion lab up there.
I don't know. Maybe she's confused.
Oh, okay. Okay. Oh, I'm sorry. I thought so. There were people standing around. I meant to check that. Yeah. Good. Thank you. So just reiterate, office hours today, we'll have this class in the middle of office hours. Then we'll have, tomorrow I have no office hours. Monday will be normal. Tuesday, Tuesday, office hours basically will be then between 1:45 and 3:15.
You gotta remember though, we gotta make sure to start, if we're gonna do a makeup class today, we gotta make sure to start it before it'll conflict with your evening class.
Right, exactly, right. So that anytime starting before 2:45. No, actually 2 o'clock. Because 2 o'clock to 3:15, that wouldn't give me any time in between, but we could do it that late. So if we start any time before 2.
Hopefully do it 1:15 or something.
Yeah, that would be fine. 1:15, 1:30, anything.
Get an hour for lunch.
Yeah. Okay. And then next week, on Thursday, office hours get changed again because I got a faculty meeting, 2:30 in the afternoon.
Friday,
So
Veterans Day.
What's that?
And then the Friday after that is Veterans Day.
It's Veterans Day. So screwy couple weeks here as far as office hours go. All right. I already marked the roll. Oh, you know about the announcements, right? Tutors, bookstore hours, Math team not meeting this week. And cafeteria menu today is fish and short order. Tomorrow short order only. Okay. All right. Any questions? Anything else before we get started? Okay. We were on page 131, section 4.2, reduction of order. And this was a second solution for formula 5. I'm trying to find their formula 5 here. Oh, that was just above there. Okay. Here's what we had. This is on page 131. Okay, example 1 in this section was, given that y1 is equal to e to the x is a solution of, oh no, this is a completely different problem. Okay, example 2. But here's what it said. A second solution for formula 5, and formula 5, by the way, was,
good old formula 5.
yeah, used to be a race car or something, I don't know. y2 is equal to y1 of x, and y2 is a function of x as well, times the integral of e to the minus integral of p of x dx, our good old integrating factor, divided by y1 squared of x dx. Don't know if you remembered, that's what it turned out being. Okay? Now, let's do, this is a second solution using this formula. So here's a function. Okay? y1 equal x squared. They tell us, without telling us why or how or anything, that that is a solution to x squared y double prime minus 3xy prime plus 4y equals 0. And again, that's a second order linear homogeneous differential equation. Okay? That's what that is. That's what these type of things do. Now, they say that y1 is a solution for that. I'm a cynic, so I always like to check and see. y1 prime would then be 2x, and y1 double prime would be 2. Okay? Well, let's see what we would have. If we plugged in 2 there, that would be 2x squared minus 3x times 2x plus 4 times x squared. The question is that equal to 0? Okay? This would be a 2x squared minus 6x squared plus 4x squared. Sure enough, that is equal to 0. Right? All right. So we verified that was a solution. All right? So that wasn't part of the problem. I just erased more than I was supposed to. Sorry about that. I'll write it back. Okay. What's that? Yeah. Okay. Now, y1. Okay. y1 is equal to x squared. Okay. Now we're going to use that result we have here. They call this formula 5. Use that to come up with my y2. All right. How would we begin?
Well, if you wanted to set it up, we know that the y1 of x is already taken care of, so we're probably going to want to look for the p of x.
P of x. And what is that? Do you remember?
It'll be in the equation, right?
Yeah, it's in the equation, kinda. How?
It was like a coefficient.
of the middle term when the coefficient of the first term was 1. That's it. So what we do here is divide by x squared. Okay, because that's the coefficient, not because that was your y1. That just happens to be that's the same here. Okay, so this will be, got it. Okay, so rewriting it in this form tells us that p of x is equal to,
so the x in the middle term goes out, right?
what's that?
You crossed out the x in the middle term.
One of the x, yeah, the x in the numerator and one of the x's in the denominator. Okay, so that'll be minus 3 over x. By that?
Yes.
Okay. So what do we do with that? We take the integral of that, and I'll do it like this. Okay, I'll forget about that now. This will be minus 3 log x. You buy that? Okay. Now, don't worry about adding a c to it. We'll do all that at the end. Okay? All right.
That's the trickiest part.
Yes. Okay, now we take e of that. So e to the that, well, to clean that up a little bit, that would be e to the log of x to the minus 3, right?
The e in the natural log.
Second?
The e in natural log.
Yes, because they've been dating. Okay, so that gives us x to the minus 3. So we've done the e. Now we integrate that integral of x to the minus 3 dx. And what would that be?
That would be x to the negative 2 over negative 2.
X to the minus 2 over minus 2. So sure enough, we could write that as minus 1 over 2x squared, if you wanted to. I'm not saying that's the best way to do, but you could if you wanted to simplify that a little bit. All right, now what we do is the integral of that thing. Let's take the minus 1/2 out front, and you have a x to the minus 2 over
So I was kind of confused as to why we took a second integral. So
Okay.
I know we took the first one because
Okay. Oh wait, did I do too many?
I think you.
Oh, I did do too many. Sorry.
Yeah.
Well, I didn't do it completely. Sorry about that. Let's start over. Okay, not all the way over, but whoa.
You just like using the eraser.
All right. All right. Sorry about that. We did e.
It should have been. The,
Yeah. Okay. We got e to the integral, and that gave us that. Okay. This is where. Let me do this part over there, because it would make more sense. That's what I was starting to do. I just got carried away doing it too many times. All right. So this will be the integral of this thing, x to the minus 3 over y1 squared. Well, y1 squared is x to the 4th. So then we have x to the minus 3 times x to the minus 4 is x to the minus.
I thought it'd be over.
Okay, it is. Yeah.
It would be 1 over the x to the 3 times x to the 4.
Okay. It would be x to the minus 3.
Oh, you brought the negative. You brought the 4 into the numerator.
Right.
Okay.
Yeah. Right. I was just doing it all at once. Okay. And that would be dx. That's the integral we're doing now. Sorry. Okay. And that would be what?
That would be x to the negative 6 over negative 6.
Okay. Which would be negative 1 over 6x to the 6. Okay. If you wanted to do it that way. Okay. So our y2 is equal to what? y1, which was x squared, times a negative 1 over 6x to the 6, and that would be a negative 1 over 6 x to the 4th. Okay. Now, okay. That's our y2. Wait a minute. Okay. How did they get an x to the 3rd rather than x to the minus 3? Did I mess something up there?
We're on example 2, right?
Yeah.
They got a 3 instead of a negative 3 in front of the log.
Oh, there is a minus in front of that. I forgot. Okay, sorry. There's a minus there and a minus there.
Oh.
That makes for a plus, plus, plus. So rather than having, okay, that makes things a lot better. I was going to say this has gotten way too complicated, and I couldn't see why. So let's do this one more time.
Where are we starting from?
Starting back from e to the minus integral is x cubed. Okay. All right, sorry about that. So then the outer integral here is that numerator is x cubed over x to the 4th dx. That's where they got the integral of dx over x, which is log x. Okay? And then you multiply that by y1, which was x squared. So we have y2 is equal to x squared log x. Okay. Now, we got our y2. So the general form for the solution, and by the way, this solution is good from, here's Victor. Victor, a couple of changes from what we talked about last time. I think I told y'all last time that I was going to, because I have a doctor's appointment next Tuesday morning, okay, I was going to have a makeup class for my 8 o'clock class this afternoon at 12:30 to 1:45. That's when they said they wanted it on Tuesday. Today they said, nope, they can't make it. So what we'll do is have the makeup class for the class we'll miss from this class next Tuesday. We'll have that sometime this afternoon. Can you be here for that anytime between 12:15 and 2? No. Okay, I'll record it all on Screencast-O-Matic, so it'll be out there on YouTube sometime this afternoon, probably. The trouble is, if it doesn't get loaded by the time my next class starts, it won't be in the playlist. It'll still be on YouTube, but not under the playlist. You'd have to go look for it. Sometime tomorrow morning, knock on wood, I'll get it into the playlist. If I can't get it done this afternoon, I'll get it done tomorrow morning. Tomorrow morning, I've got a treatment, so I won't be on the Birmingham campus at all tomorrow either. I hope to be able to get my work done while I'm there. Last time, the wireless is not great there, but it's okay. It's a public system, so it goes a little squirrely sometimes. But I was able to get everything that I could do done yesterday at that time, except emails. I got some of those done, but then Benadryl knocked me out, so I wasn't able to do it anymore. So hopefully I'll be able to get all that kind of stuff done tomorrow morning. So sometime, say 7:30ish or so tomorrow, hopefully it will be in the playlist. Today's class and that class. Hopefully today's class will be there sooner, but we'll see. Okay, that's today. So next Tuesday, no class, none of this class at all. And you're not in linear algebra, right? Okay. So you don't have to come up here Tuesday morning at 9:30. I'll probably still be at my doctor's visit then. I'll probably get back to campus before class will be over. We'll get the whole class covered this afternoon. So you can listen to it then instead if you want to do it then. Should be in the system by then. All right, then Thursday, I have change of office hours because we've got a faculty meeting. Oh, wait, let me back up. Tuesday, normally I have office hours starting at 12:15 to go to 3:15, but then my 8 o'clock class, 12:30 to 1:45, I'll make up their class on Tuesday. So my office hours on Tuesday will be 1:45 to 3:15, okay? Then Thursday, we have a faculty meeting at 2:30, so my office hours are 12:15 to 2:15, because I have to go to the faculty meeting at 2:30, then I'll come back and teach my class. And then next Friday is Veterans Day. There are schools closed next Friday. Not tomorrow, but next Friday. So that. All right. So here we came up with it. We just did example 2 on page 131. They gave us Y1. We calculated what Y2 was using the formula above. And now we can do the general solution will be Y is equal to some C1 Y1, which is x squared, plus some C2 x squared log x. That's our general solution for that differential equation. Okay.
There's no way to get those C's.
What's that?
You can't get the C's. We're unable to find C.
Unless you're given initial conditions or boundary conditions or something like that, then you can find it. Yeah. But yeah, without giving any more than just this is a differential equation, yeah, all you get is a general solution.
It says on the interval from 0 to infinity, but you would need like what?
Oh, okay, yeah, that's what I was talking about before. Why is that 0 to infinity? And that's 0, yeah, because log x is part of your solution. That's not defined for x equals 0 or anything negative. So it has to be 0 beyond 0, not even counting 0, beyond 0 and positive. That's why the integral. And unless you were given some initial conditions, like initial placement, initial
like
first
y
group.
at 0 equals.
Yes, exactly. Some type of 2 pieces of information you can solve those. Okay. All right. The derivation and use of Formula 5 has been illustrated here because this formula appears again in the next section, and again in 4.7, and again in 6.3. We use 5 simply to save time in obtaining a desired result. Okay, blah, blah, blah. Reduction of order can be used to find the general solution of a non-homogeneous system, A2x y double prime plus A1x y prime plus A0x y equal g of x whenever the solution y1 is associated with the homogeneous solution. That solution is null. Okay. So homework exercises here, any of the odds 1 through 15. Do either 17 or 19 or both. And you can look at then 21, any of the others you want to. You don't have to do anything with those. Now, let's go to 4.3. This looks like and feels like and hopefully is a step in the easier direction. In fact, I don't see why they do this. 4.2 was dealing with variable coefficients. 4.3 is going to be constant coefficients. So hopefully we can use what we had and step back and do something a little easier. Okay. Okay, blah, blah, blah. In this section, we'll see that the foregoing procedure can produce an exponential solutions for homogeneous higher order differential equations that are written in this form. Let me get this off of here. And here's the form we're going to be dealing with in this section. A sub n, not a function of x, just a constant a sub n, y to the nth derivative of y, plus a sub n minus 1, y to the n minus first derivative of y, plus dot, 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 all the way down to a sub 1 y prime, plus a sub 0 y, and we'll set these homogeneous for now, equal to 0. They put a couple more in there, one more in there, I did. Now, where the coefficients of ai, where I goes up to n, and n is the maximum derivative that you have there. Sorry. These are real constants, not variable constants, real constants, no imaginary constants, real constants, and the a sub n is not equal to 0. Because if the a sub n was equal to 0, they wouldn't be in nth order. It would be in minus 1 order. Okay, so that's the restriction there. So we start off with an auxiliary theorem, auxiliary equation here. We begin by considering the special case of a second order equation. AY double prime plus BY prime plus CY is equal to 0. Now, why did they change from A subs to B and C? I don't know. It doesn't matter. They're just constants. So don't let it bug you. Okay. A and B and C are all constants, but we're basically going to say A isn't 0. Okay. If we try to find the solution, and this is a good thing to try, y is equal to e to the mx. Okay? Why? That's our favorite formula of all time. It's our function of all time. The exponential function.
As long as the m is 1.
If the m was 1, it would be our most favorite, but we can't have it that restricted. Okay? So let's assume that's going to be one of a solution. Okay? Let's see if it works. Okay? Y prime would be m e to the mx, right? And y double prime would be m squared e to the mx, right? Then our differential equation would be a m squared e to the mx plus b m e to the mx plus c e to the mx is equal to 0. Notice anything about this? As in the F word? You can factor out e to the mx, right? So do that. E to the mx. And what do you have left? am squared. bm. Yeah, exactly. Okay. Now, if this were back in algebra and you're solving this, you say, okay, let's set each of those equal to 0. But guess what? E to the mx is never, ever, 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 ever equal to 0. E to the mx approaches 0 for either very small m's or very large m's, one way or another, depending on plus or minus, but it's never equal to 0. Always positive. Okay? So therefore, your only possible solution would be then if this thing were equal to 0. Well, what is that? That is a quadratic equation in variable m. And you can use factoring, quadratic formula, or anything else like that to find those zeros, okay? So that's what we do. That thing equal to 0, okay? That's called the auxiliary equation for this differential equation, okay? Okay? Now, without knowing anything else, you'd almost have to use the quadratic formula, and what would you get then? M is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. There is your possible solutions, okay? Now, there will be 3 forms of the general solution, okay? And this basically gives you 2 solutions. They call it M1 and M2. So let me get in the same mode that the book is in. Let's take out the minus down here, and we'll call this M1. Is that with a plus sign, and M2 is minus b minus the square root of b squared minus 4ac over 2a. Okay, those are your 2 possible values for M1 and M2. Now, we have 3 possibilities here. Either M1 and M2 are real numbers and distinctly different numbers. Now, what makes those real numbers?
There's no I involved.
Okay. And where would I come into play here? If there was a negative inside here. So if that, remember we used to have a name for that called the discriminant, b squared minus 4ac. If that is positive, greater than 0, then M1 and M2 are distinctly different, real numbers.
But if it's negative?
If it's negative, then they're distinctly different complex zeros. Okay? If it's equal to 0, you have a double root. Okay? Both roots are the same. It would be minus b over 2a. Okay. And that would be real. Okay? So either M1 and M2 are real and distinct, if that discriminant is positive. M1 and M2 are real and equal, that's if the discriminant is 0. M1 and M2 are complex conjugate numbers if that discriminant is, negative. So let's see what happens in each case. Okay, the first case, if they're real and distinct, then your solution is y is equal to C1 e to the m1x plus C2 e to the minus m. Wait, no, let's just leave the m2x. I don't know why I was wanting to make it a minus m2x. Yuck. Okay. Yeah. Those are 2. This is our general solution for these 2 real and distinct solutions. Now, hint. If we were to go back to, let's see how far back to go. when I was doing them, I said, okay, I told myself, okay, pay attention to this. And now I can't remember where they were. Okay. What's that?
So I just start wearing long sleeves.
Yeah, I know. It's just crazy in here. I had people griping all day yesterday. Ah, here we go. Example 7. Okay.
Example 7 on where?
On page 124. Okay.
That wasn't that long ago.
And example
I was looking at that.
9. Notice here they say, okay, notice here are some solutions. And what form are they in? E to the mx, e to the mx, e to the 9, e to the mx, e to the mx, e to the mx. So guess what? That's where they came up with these when this was the case. That's why they could pull those out, and that's why it griped me at the time. They said, why don't they go on and tell you where you get these, okay? That's where you get them, okay? So, there are probably others too, but I just wanted to point that out to you. Okay, so when the discriminant is positive, then you have two real distinct solutions, okay? And that's what your general solution would be. Now, what if you had repeated real roots when M1 was equal to M2? In other words, your discriminant is 0, and that is minus b over 2a, is what it turns out being, okay? We necessarily obtain one exponential, which would be y1 is equal to, this is when the discriminant is equal to 0 when you have a repeated root. So y1 would be that first root, and they don't do anything special about it. They just call it m1. So y1 is equal to e to the m1x. Okay? Now, but you got to have another one, okay? But we know that m1 is minus b over 2a. So this is y1 is equal to e to the minus b over 2ax. Yuck. Okay. You can plug in those values and get exactly what they are. Okay. Now, if you go back to 4.2, equation 5 in 4.2, I've gone too far. Oh, that's the one we were just working on. There it is, just one page back. There at the top of the page. You see your y1 is going to be the first part of that. So when you have y2, you're going to have an e to the minus b over 2ax in there because that's your y1. But then you're going to have an integral, okay? So that's the first part. The second part, and it's a voila here, if we went into that formula and did all the mess that we had to do with it, okay, you wind up with that numerator or that big integral just producing an x. So your y2 is just going to be x. Yuck! X times that. What's that? Yeah, no. Sorry. And then, if you happen to go back to, say, example 1 in that section, page 130, once you had, no, that's not the wrong one. What was the one we were talking about before? There was one we did. I was certain we had one like it, but I can't see it now. I can't see it. But it was maybe it's my imagination. I thought it was. Then when you have one solution and we only have that one value for m, then you just multiply the variable times that first solution, and that gives you one. Okay. It just works out that way. I just don't know if it's worth doing the time. Let's take the time to do it. Okay. Let's go back to our equation 5. And remember, that's the one that you had the integral of e to the minus integral p of x dx. My pen is very, very slow here. Over y1 squared. Okay? Let's do those things. Your p of x in this case is trying to find my, oh, here we go. Okay. Is basically b over a, right? If you divide by a, your p of x is b over a. Okay. Now, the integral of b over a would be b over ax. Okay. And you have minus that, because it's minus that, e to the minus that. Okay. And then you have that divided by e to the minus b over 2ax. Okay, because you divide by y1 squared. Okay, except I didn't square it, did I? Yes, ma'am. I'm sorry, I can't hear you. Oh, okay. Do you need graph paper? Okay. Too deep. I'm going to drop everything in a minute. There's one copy, yeah. Okay. You don't need graph. Okay. I just can't conceive of walking in a classroom. You know, the class is going on to do it, but anyway. Okay. Sorry, this has gotten sort of jumbled here. This thing we were supposed to square, and I don't have enough room. If you squared that, that would be minus e to the minus 2b over 2a. And that, the 2's go out then, and you have e to the minus b over ax here and there. So basically, you have the integral of dx. Okay. Yeah. Okay.
No, that's part of the.
Yeah, that was part of the explanation before.
I was like, what happened to it?
Yeah. So that integral just turns out integral of dx, which is just x. Okay. So that's what you multiply by your y1. Okay. That's where it comes from. Now, I don't know if it's worthwhile to show that, but yeah, indeed, that's where that's how it gets there. Okay. So hopefully that didn't take too long. So those are your two solutions then. if your M's are distinct, here's what they have. If M's are not distinct, here's what you have. Okay? Now, they don't say e to the minus 2b over 2a. They just call it M1. What if we have the complex conjugate roots? In other words, your M, the discriminant is negative, so this comes up being a complex number, a real part and an imaginary part. Okay? That's case 3, bottom of page 133. And I think by now I've got to go to a clean page. I should have probably done it earlier, but it still had stuff on it we needed, if I can get it to go. Actually, I probably should erase just parts of this.
Just erase it all.
Okay. You'll just have to remember what those pieces are. If M1 and M2 are complex, then we can write M1, and the complex conjugates of each other, is equal to, they use alphas, I was going to use A, alpha plus I beta, and M2 is equal to alpha, they don't subscript them, yeah, alpha minus I beta. Okay. Because they've got to be complex conjugates of each other, so whatever the alpha is, it's the same in both. The betas are the same except for the sign. Okay. Now, if you write out your solutions then, y, just like we did before, now this time they're going to use a capital C1 as opposed to a little c1 they did before. And the only reason I can conceive of this is that either just to distinguish between the two or to maybe emphasize even these coefficients could be complex numbers. They haven't said that yet, but okay. But we'll do capital C1, e to the, and then you do the M, which is alpha plus I beta x, plus C2 e to the alpha minus I beta x. Those would be your two solutions, just like they were in distinct real solutions. Here's your distinct complex solutions. However, these are required to be complex conjugates of each other. So not just M1, M2, but these numbers.
That makes sense.
Yeah. Right.
The way the quadratic formula is similar.
Right. However, in practice, we prefer to work with real functions instead of complex functions. And to that end, we use Euler's formula. Now, he has a lot of formulas, but here is his formula. E to the I theta. Believe it or not, this is cosine theta plus I sine theta. An extraordinarily somewhat simple but almost revolutionary type formula. Now, here's something else that makes it bizarre. What if theta were equal to pi? The
Cosine would be -1, sine would be, sine would be 0.
okay.
So -1 plus I, or no, -1.
Yes.
And then E equals
Yeah.
a number.
And then you have this thing. E to the I pi is equal to -1. Okay.
If that I wasn't in there, I'd be really concerned.
Okay. Yeah. Oh, yeah. Absolutely. But this is pretty incredible. What are our two most famous complex irrational numbers? Pi and E. And this is our imaginary element, I, and then a number 1. So you have a real number, two irrational numbers, two most famous, and your imaginary unit in one little formula It's just about as simple as you can make it.
I has a square root.
Right.
So how does that work out to be the square root of negative?
From here. Now, that was where the proof was. I mean, yeah, that is the tough part. But once he did that, then plugging in pi, you come up with this, and you go, oh my goodness. Here are 3, you might even say 4 of the most fundamental single numbers in the world, ever, and they're related by this one simple little formula.
E to the I equals negative.
Yeah, pretty incredible. Okay. Now, it comes from the Maclaurin series, and I don't know if I think we touched on it in Cal 2, just with a slideshow type thing. I can't remember the chapter. It was Infinite Series. Was that chapter 10? I think.
Yeah, we started this the Cal 3 class in 11.
Yeah, so I think it was chapter 10. I'm not sure, but it's somewhere back there. You can go back and find the Maclaurin series and see this, and sure enough, you come up with that Euler's formula. Okay, can derive it that way, and then plugging in, you get this one. Okay, now. Here is why we even introduce that. E to the I theta is cosine. No. Okay. Let's rewrite what we've got here. E to the alpha, E to the I beta, I'm sorry, that would be alpha x, e to the I beta x. Okay? That would be this term, right? And then you have e to the alpha x, e to the minus I beta x. That would be from that term, right?
Yeah.
Okay. Principal properties of exponentials, okay?
And that would be y equals all that?
No, yeah, you'd have to go back and plug. If you wanted to do that, that'd be y is equal to c1 e to the alpha x e to the I beta x plus c2 e to the alpha x e to the minus I beta x. Okay. Now, let's use Euler's formula here, but let's rewrite it as e to the I beta, okay, x, okay? So everywhere you see a theta, you put a I beta, you put a beta x, okay? So it'll be cosine beta x plus I sine beta x, right? Okay. And let's also write e to the minus I beta x. That would be cosine of minus beta x plus I sine of minus beta x. Yuck. Okay. Do you buy that? Just instead of theta, we put in a minus beta x. Okay? Well, because cosine is an even function, this is the same as cosine beta x, right? Minus, because sine's an odd function, minus I sine of beta x. Goodness gracious. Okay. What's that?
Is that number
Yes, me too. I've got a smaller sheet than you do. Okay. All right. So now let's plug this into our formula here. Y is equal to C1 E. Let's pull out a E alpha X. I'm tired of writing it. Okay. Okay.
E alpha X.
E to the alpha X. That showed up in both of them, right?
Yeah.
Okay. Okay, so let's pull that out. E to the alpha X. Okay. And then we have C1 e to the I beta X would be cosine beta X plus, this is all in parentheses, I sine beta X, right? Plus C2 times e to the, we already pulled out the alpha X, e to the minus I beta X, which is down here, and this would be cosine beta X minus I sine beta X. Okay. Okay. Now, I realize I've forgotten to do something I should have done. Let's forget the C1s and C2s for now. I know it doesn't seem fair, but if we did that, yeah, but we could say they're equal to each other and pull them out, or something like that. But now what happens? Look at this. You have a I minus I sine beta X and a plus and a minus. Those go away, and what we're left with is just real numbers. We lost the imaginary part of anything. Okay.
If C1 and C2 are the same.
And what they did was say, since that works for any choice of constant C1 and C2, we'll choose C1 equal C2 equal 1. Okay? And then we'll choose another one, C1 equal 1 and C2 equal minus 1. And when you do that, here's what you get as your solutions. You get Y is equal, in the first, the first case we got what I just wrote down there, and that was e to the alpha X, okay, that was what we pulled out. When C1 equals C2 equal 1, then you just wind up with times 2 cosine beta X. Yuck! Quit. Okay. Because when the C1 and C2 are equal, you have 2 cosine beta X, because I sine beta X went away. Okay? So you could rewrite this as 2e to the alpha X cosine beta X. Okay. Now, that would be your Y1. You choose your Y2, and this is not comparable. Sometimes they say they're arbitrary, but other times they say, but choose this, you know. And if you did choose that, C1, 1, and C2 minus 1, then what you have is Y2 is equal to e to the alpha X. Okay? And if you have them opposite with each other, this is 1 and this is minus 1. Yuck. In this case, your cosines go out and you're left with I signs, right? Because, and that would be 2 times I sine beta x. Okay. Okay. And then they pull the 2 out front. 2 e to the alpha x I sine beta x. Well, I don't need that last parentheses, I guess. Okay. Okay. This is the magic of Euler's formula, okay? If you can choose those coefficients, okay? So, a corollary to theorem 412, which was somewhere way back there in section 4.1, the last 2 results show that let's go back to 412. Theorem 417, boy, 4.1 had a lot of theorems in it. 411, 412 is on page 120. Okay. If all those are solutions, blah, 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 the linear combination is a solution. Yeah. Oh, the corollary. Okay, top of the next page. A constant multiple, y is equal to C1, Y1, X of a solution. Still don't see how these are very useful. But anyway. They drop the i's, and I can't for the life of me, well, wait, yes I can. Equation 2, no, that's, hold on. I was on the wrong page. What's that? That sound?
It doesn't sound very well.
That outside?
I guess the AC or whatever.
You think that's this? I thought that's the sound on the outside. It's not. My hearing's so bad.
That little room. Yeah, that little room.
Right next door?
Weird noise.
Okay. Well, maybe y'all wish the air conditioning would quit. You got your wish. Okay.
I don't think it's quit. Well, maybe.
I don't know.
Doesn't feel much better.
Now, here's the part that, I mean, I believe them. I know it works because I've used it. But I don't see what they did with the i's. Okay? Notice here the y2 has an I with the sign. But then when they write the general solution, they leave off the I with the sign. And I can't remember how you rationalize that. Okay? I know it's in there somewhere, but I just can't.
They got rid of the I off the sign?
Yeah. And it may be because your e to the I sign had an I in it, and maybe that wipes out that I. I don't know, but anyway, this, yeah. So your general solution then would be y is equal to, this is when you have complex, when you have the discriminant being negative, okay? Here's what it comes down to. y is equal to, now this C1 is not like those capital C1s that you got to choose. This is your general solution. E to the alpha x, okay? Okay? And remember what the alpha was? That was from the complex parts here, okay? And maybe that's what happened to it. E to the alpha x cosine beta x, okay, plus C2 e to the alpha x sine beta x. Real solutions that came from those complex solutions, the complex conjugates of each other, okay? So basically, even when that M turns out to be complex, Euler's formula flips it around, and by substituting sines and cosines in there, the imaginary part there becomes a real part, okay? That part was always real, but you lost the eyes, okay? So basically, there's your three situations, okay?
Now that we've lost the eyes, the equation can't see anymore.
Exactly. No seed potatoes either, okay? So, let's do example 1. Solve the following differential equations. Whoa, it didn't disappear, did it? Okay. This is being ridiculous. There we go. All right, solve the following differential equations. 2y double prime minus 5y prime minus 3y equals 0. Okay? What's your first shot? Okay, you don't have to do that in this case. You suppose a solution, let y equal e to the mx. You assume that's a solution, right? That's what we did before. Then y prime is equal to m e to the mx, and y double prime is equal to m squared e to the mx. So now this becomes 2m squared e to the mx minus 5m e to the mx minus 3e to the mx equals 0. And obviously e to the mx can't be 0, so you have 2m squared minus 5m minus 3 equals 0. Can we solve that for m? Well, you can try factoring if you want to. 2m times m plus and minus, I got it in the wrong place. Okay. Okay. And make that, let's see, a 1 and a 3. Let's see, is that right? It's not, I know, but that'd be 2m squared, yes, minus 6m plus 1, yeah, that's right. Plus 5m, or minus 5m, minus 6. Okay? So what are your m's? Negative 1/2 and 3. Okay? So your solution would then be y is equal to C1 e to the minus 1/2 x plus c2 e to the 3x. Okay. Now, that was pretty straightforward. Okay. Second?
Much easier than the last section.
Right. Okay, that was the first thing we did in that when those were distinct. Okay?
So the B part?
Now let's go to the B part. How are we doing on time?
We got about 2 minutes.
2 minutes. Think we can do the B part? Okay, let's try it. Okay? All right. Y double prime minus 10y prime plus 25y is equal to 0.
So we want to assume that y equals
E to the mx. Now can we skip the other part and just write what they call the auxiliary equation? That'd be m squared minus 10m plus 25 equals 0.
Yeah.
Do it a few times, you'll see. That's what it comes out. Factor out the e to the mx. And what does this give us? Yes, m equal m equal 5, yeah. Okay. Yeah. Right. So what would your solution be? Y is equal to C1 e to the 5x plus C2. Remember, this is where you x e to the 5x. If that's a double root, then doing that integral, that's when you divide by, well, you already got it. Your p of x is equal to minus 10. The minus the derivative of that would be, the integral of that, that's when you do that middle part. And it always comes up, flip back a page, it always comes up, case 2, y is equal to c1 e to the m1x plus c2 x e to the m1x. Just an extra factor of x in there. It will happen. It works. We did it in the generic case. It worked.
Double root, throw an x in front of the
Throw
second.
x in front of the second. You got it. They have the same arguments for the e's. You just have one with an x and one without an x. Okay? Now, and that's exactly what they got there.
We're out of time.
Okay, yeah. So we'll begin next time on C.
Later on today.
Yes, later today on C.
Didn't know I was going to be getting a double dose of MTH2 today.
What a happy day, huh? Okay. Let's see if there are any homework exercises here. We almost got through 4-3, I think you can do any of the odds 1 through 13. Yeah, just do those. And we'll pick up some of the rest of those later this morning, or this afternoon, earlier this afternoon. All right, rolls just like before. APP, AA.